So hi, I'm Janice Gobert. I'm co-director of Learning Sciences at WPI and the CEO of a small startup called Apprentice, which I started with two former graduate students of mine, Mike Salpedro and Cameron Betts. And I'm a cognitive scientist by training, and I'm very interested in the design of learning environments that can offer real-time support to students and real-time assessment metrics that teachers can use to do data-driven decision-making.
It is my great pleasure to talk today to Janice Gobert. She's an associate professor and co-director of Learning Sciences and Technology at WPI. She's a well-known researcher in the area of cognitive science, instructional technologies, and assessment. She's been especially active in the area of educational data mining and learning analytics recently. So Janice, could you share a bit with us what you are doing with learning analytics?
Yes, thanks. So what we're doing is we're trying to do real-time skill assessment for science inquiry aligned to the next generation science standards. So we want to assess, how students are making a hypothesis, if they're designing controlled experiments, collecting data accurately, interpreting that data accurately, if they can warrant their claims using the data, and then can they communicate their findings.
That sounds very interesting. So what kind of methods, in particular learning analytics methods you are using, what type of data you are collecting, and how those methods help you to understand better learning processes happening?
Great. So what we did, my group designed a series of microworlds aligned to the content areas for next generation science standards. And these have variables that students have misconceptions about. So what we're trying to do is give them opportunities to understand this content more deeply by guiding them through the inquiry processes. Then what we do is we use real-time data analytics to analyze what the students are doing, and we can jump in real time. So we can provide the teacher with metrics that he or she can use, and then we can also jump in real time via a pedagogical agent. And so the principal method that we're using is text replay analysis that was developed by Ryan Baker. And what we do is we pair that with machine-learned methods to generate these EDM-based algorithms that can react in real time.
So how would you compare the types of insights and results you are getting to the traditional cognitive science methods that you and many other cognitive scientists were trained in?
So many psychometric models are undergirded by item response theory. And item response theory has a really hard time calibrating what the student knows as the student learns within the learning environment. So that's particularly problematic because they're in a learning environment, they're acquiring knowledge in real time, and what we're hoping is that our metrics can actually calibrate what the student's learning as they're going through the environment, right? So they're much more sensitive. The other, another important difference is that when a student makes a hypothesis, all their subsequent inquiry is related to that hypothesis. And the reason that then creates a problem for using traditional IRT methods is that there's dependence across the various subtasks.
Excellent. That sounds really exciting. So obviously a lot of interesting insights are obtained in that sense. So what kind of success stories you can tell us about your research and the types of impact that you made in actual practical work?
Well, as I said, we've designed these micro worlds, and we've shown a few things. So one of the more difficult areas is trying to figure out if students can design controlled experiments. By that, what we mean is they're actually changing the target variable and keeping all the rest the same. So that's a classic, what we call control for variable strategy. We refer to this as designing controlled experiments. And what our metric does is, regardless of the ways in which students conduct trials, that is, they don't need to conduct them sequentially in order for us to generate a metric that says the student knows the skill or doesn't know the skill. So this is a major advance over other methods which have used an approach called knowledge engineering, which requires the student conduct either sequential trials, so they do trial 1 and then they compare trial 2 to trial 1, or the student will do a whole bunch of trials, and the system has to maybe infer that the child really meant trial 1 versus trial 8. But you're not in the mind of the student, so you actually have a very hard time using knowledge engineering in order to come up with a metric that can decide if the student knows the designing controlled experiment skill. So these previous techniques via knowledge engineering are either sort of too lenient or too stringent. So using EDM, we've been able to generate an algorithm that can determine whether the student knows the skill regardless of whether they've done sequential trials. So some other work that we're doing in our lab is we're actually detecting various affective states of the learner. So we know if they're bored, we know that whether they're confused, whether they're frustrated, whether they're very off track. And this is an important aspect about learning in real-time environments because you want to react to students' affective states. This is just as important, perhaps even more important, to their skill level, right? From the point of view of designing learning environments. And also from the point of view of assessment environments, because you want to know when you have that metric if it's really a good, valid assessment of what Johnny knows. If Johnny's extremely frustrated on a given day, you probably want to know that, right? And so I think in the future we might actually incorporate some of these features into our assessments. We're certainly starting to incorporate some of these features into our learning environment.
Excellent. Thank you very much for taking time to talk to us and
You're
share
welcome.
your experience. And we look forward to learning more about your research in the future. Thanks.
Great.